Have you ever just, stopped and really thought about electricity? I mean, it's just one thing, right? A simple flow of current. And yet somehow it performs all these different kinds of magic tricks all over our homes. So today we're going to pull back the curtain and see how it works.
How is it that the very same current that's powering your phone can also make a metal coil glow red hot and heat up an entire room?
And then, how can that exact same current turn around and create motion, spinning the blades of a fan to cool you right down?
Seriously, just look around you right now. The light you're using, the screen you're watching this on, it's all running on this single invisible force.
So that's the big question, isn't it? Well, it turns out that electric current basically has 3 secret powers that make all of this possible. And today we're going to reveal every single one of them.
Let's kick things off with the one that's probably the most familiar, the one you can actually feel. Its power to create heat.
So the key word here is resistance. The best way to think about it is like friction. As that electric current tries to shove its way through a material that's pushing back, that struggle generates heat. The material is literally getting hot from all that effort.
Now, scientists have a really precise way to figure this out. It's called Joule's law. And don't worry, you don't need to memorize the formula. But what it tells us is pretty cool. The heat, that's the H, depends on the current, the resistance R, and how long it flows. And notice the current is squared, which means more current or more resistance equals a lot more heat.
And what's so clever is how engineers actually use this. Instead of trying to get rid of resistance, they pick materials with super high resistance on purpose. Things like nichrome, which you'll find in electric heaters and stoves, are specifically chosen because they are designed to get incredibly hot when you run a current through them.
The old-school incandescent light bulb is the perfect example. There's this tiny, super-thin wire inside made of tungsten. It resists the current so fiercely that it heats up to almost 3,400 degrees Celsius. I mean, it gets so ridiculously hot that it actually starts to glow, turning that electrical energy into both light and, as you know if you've ever touched one, a ton of heat.
But this power can also be really dangerous. In your home's wiring, you've got these 2 main wires, a live one and a neutral one, and they're kept apart by a plastic coating. Well, if that plastic wears off and they touch, you get a short circuit. The resistance suddenly drops to almost nothing, the current shoots through the roof, and the wires can get hot enough to start a fire in seconds.
And that is where these little heroes come in. A fuse is basically a planned weak link in the system. It's just a special wire with a really low melting point. So if the current ever gets dangerously high, that little fuse wire melts before your walls can catch fire. It breaks the circuit, shuts off the power, and basically sacrifices itself to save your house. Pretty cool, right?
Okay, so that's heat. Let's move on to the next power, which is, well, it's a lot more mysterious. It's the power to create an invisible field of force, magnetism. For the longest time, everyone thought electricity and magnetism were 2 completely separate things. That all changed back in 1820 thanks to a scientist named Hans Christian Ørsted. He was the very first person to figure out that they were deeply, deeply connected. What Ørsted discovered was actually pretty simple. He saw that when he passed an electric current through a wire, the needle of a compass sitting nearby would start to move. And since a compass needle only moves when it's in a magnetic field, there was only one possible conclusion: electricity creates magnetism. So how do you know which way this invisible magnetic field is pointing? Well, there's a really simple trick for it called the right-hand thumb rule. Go ahead, try it. Imagine holding the wire in your right hand. If you point your thumb in the same direction the current is flowing, the way your fingers naturally curl around the wire, that's the direction of the magnetic field. It's a super handy way to picture this invisible force. Okay, so what if you take that wire and instead of leaving it straight, you wind it up into a tight coil? Well, that's called a solenoid. And by doing this, you're concentrating that magnetic field. All the little fields from each loop add up, and what you get is a strong, steady magnetic field right down the middle. You've just made an electromagnet, a magnet that you can turn on and off with a flip of a switch.
All right, let's recap. We've got electric current making heat through resistance, and we've got it making its very own magnetic field. So for the grand finale, we're going to combine that magnetism with another magnet to unlock the third and final power, the power of motion.
This is the key question. We know a wire with current has its own little magnetic field around it. So what do you think happens when you take that wire and stick it inside the field of a different, much stronger magnet? The 2 magnetic fields basically interact with each other, and the result is a physical push, a real force. The wire actually moves.
And here's the really wild part. The push isn't in the direction of the current, and it's not in the direction of the magnetic field. It's at a right angle to both of them.
And you guessed it, there's another handy rule for this one. It's called Fleming's left-hand rule. If you take your left hand, point your index finger in the direction of the magnetic field, and your middle finger in the direction of the current, your thumb will magically point in the direction of the force that's pushing on the wire. This is the fundamental rule for how every electric motor works.
And this is it. This is the magic behind the electric motor. You just have a loop of wire sitting inside a magnet. Current flows in one side of the loop and out the other. If we use our left-hand rule, we can see that one side of the loop gets pushed down while the other side gets pushed up. And that creates a turning force that makes the whole loop spin and spin and spin.
And that one simple spinning motion, that trick of turning electrical energy into moving energy, that's what powers almost everything that moves in our world. Remember that fan from the beginning? It's just an electric motor spinning some blades. Your washing machine, your mixer, your computer's fan, they're all just electric motors doing their thing.
So we've seen how electricity can create heat, invisible magnetic fields, and finally, motion. But now, for one last little trick. A question that flips this whole thing on its head.
Think about it. If putting an electric current in a magnetic field creates a force that causes motion, what would happen if you did it the other way around? What if you took a wire and you forced it to move through a magnetic field? Could you generate your own current? Well, the great scientist Michael Faraday asked that exact question, and his answer literally changed the world. It's how we generate almost all of our power. But that is a story for another time.